Okay, welcome to the Lab4 demo from Ryan Smith and Nancy Zheng. Thought we'd start out with just the code snippets. The first thing that we can look over is just our current time test bench, which is just kind of testing to make sure that the current time, when it matches up with the set alarm by the user, it is showing an LED. So this is just our test bench. So you have the inputs here to reset the clock, the alarm hours and everything. Outputs. Here's the LED, the call to the module, and then just some scenarios just to make sure our code is working. Kind of changing the reset. Making sure that reset is working, and setting the time to be equal to the alarm, and then checking our variable buzz to make sure that the LED should light up when they are equal. Another thing that another snippet of code that we can look at is the alarm. The actual showing of the alarm and setting the alarm. So in this we have our inputs, we have the clock, the hours, and then we have the reset. So if reset is on, then alarm is set to zeros here, and if it is not on, and the user does want to input the alarm clock will be set to the inputted hours, seconds, and minutes that the user has inputted. I would say one of the major errors for our Lab4 was our inability to push it to the FPGA. Whenever we would try to generate the bit stream to push it, we would get an error saying that there was a port error. I think it was something wrong with our constraint file, because it would give us an error saying that our ports, so there was an error with our input and output ports, and suggesting that we on a pre-hook, and we couldn't really figure out what that was. But that was pretty much the major error of our lab.
Okay, so here we have our counter design module, which allows our clock to increase by 1 second. So we have a clock input, a set time input, which is activated by the user when they want to set the right time. Then we have inputs for new seconds, new minutes, new hours, which is set by the user. And then we have output registers for seconds, minutes, and hours. And we have 6 bits for the seconds and minutes, since we had to count to 59, and then we have 5 bits for hours since we only had to count to 24. So then here we just initialize a parameter called 1 second to 100 million, and then we have a clock count that we initialize to 0. And then so this just initializes everything to 0 at first, and then so then in this always block, always at the positive edge of the clock, when our 1 second counter equals 1 sec, which is the 100 million, which is 100 megahertz, the 1 second counter will reset, and then else it will increase by 1. So that's how our 1 second clock works. And then over here, this always block is where the function of the clock is really set in place. So if the user activates set time, they can input seconds, minutes, and hours, which will be set to the second, minutes, and hours of the clock. And then so in this block, so this is if clock count, so every single time it increases by 1 second. If it's less than 59, it will continue to increase by 1 second. and then once it surpasses 59, seconds will be reset to 0 and it will add 1 to minutes. And the same thing happens for minutes and hours. So when minutes surpasses 59, minutes will be reset to 0 and hours will increase by 1. And for this one, if hours surpass 24, if hours surpasses or is at 24 and minutes surpasses 59 and seconds surpasses 59, then seconds, minutes, and hours will all reset to 0. This is for a 24-hour clock format. So yeah, this is that module. So some of our successes, so although we couldn't successfully push our design to the FPGA, we did learn a lot from this lab. It was really interesting learning about clock cycles and how the different modules come together to ultimately form a clock. That is the end of our video. Thank you.